without further notice, I suggest we start up, and we're very glad to have here Pavel Perezhogin, who is going to present recent work on the use of a generative model for stochastic physics in ocean model. And Pavel, the floor is yours. That's a loose agenda, so take the time you need for your presentation. We're very glad to have you here. Thanks.
Thanks for the invitation. So I'm sharing my screen. Do you see slide? Do you see change of slide?
You see the slides?
Okay.
Yes, good.
So I can start. So this work is devoted to further development of stochastic subgrid models for ocean. I first give some small motivation slide about mesoscale eddies. So we orient on parameterizing processes which are partially unresolved in eddy permitting ocean models. So these are mesoscale eddies, which has scale 100 to 300 kilometers. They carry most of the kinetic energy. And also, we know that the generation of mesoscale eddies is connected to the complicated energy cycle, which becomes partially unresolved on a coarse grid of 1/4 degrees. There are existing parameterizations of mesoscale eddies. There is a physical parameterization by Jensen. There are also machine learning parameterization like Guemin-Zanna, and in this work we try to develop on top of Guemin-Zanna work. The plan of the talk, I first will give an introduction to the generative approach of machine learning to build a stochastic parameterization, and second I will show some offline and online tests in two-layer quasi-gastrophic model. So when we train our parameterization, we rely on the spatial filtering approach. It is large eddy simulation. So to build parameterization, we need to have a high resolution model, which is governed by some equation. Then we need to introduce Karsgarian operator. And according to this Karsgarian operator, we can introduce a missing physics term, also known as subgrid forcing. It is a commutator between filtering, which is overbar, and nonlinearity in the system, which is F. In the case of quasi-gastrophic equations, it will be divergence of potential vorticity flux. So the field which we see here is quite complicated, and it's difficult to propose physical model to predict it. Now, what we understand by the stochastic parameterization. So first of all, we need to identify the source of uncertainty. In the expression for the subgrid forcing, we have, let's look again for this expression. We have U and Q, which is not filtered. It means it depends on the state of subgrid eddies. And the state of subgrid eddies is unknown if we solve the typical parameterization problem when we have only the resolved turbulence field. And here we show an example of what we want to construct. On the left, we have the resolved turbulence field, and on the right, we have many possible samples of subgrid forcing. And the uncertainty in this subgrid forcing is connected to the uncertainty in the state of the subgrid eddies. This uncertainty can be represented by conditional distribution of subgrid forcing as conditioned on the result flow Q over bar. Here you see many samples. It's given by our stochastic model. I should say that this conditional distribution is not tractable, so I provided here only to give some understanding of what we really want to sample. There are some special cases when this distribution can be partially reconstructed. For example, if we consider Guemin-Zanna work, They use the CNN to predict conditional mean and conditional standard deviation. These are first two moments of conditional distribution, and it means that they approximate this distribution with point-wise Gaussian likelihood. Having the statistical model which predicts two moments, they can sample from this distribution by multiplying white noise field to standard deviation field. The problem with this model, which is our baseline, is that there is no spatial correlation. And we want to introduce the spatial correlation in a natural way when we do not need to tune it for every particular case. And we ought to do it by passing the white noise as an input field to the neural network, to the CNN. Once we pass the white noise to CNN, it gets transformed by CNN, and consequently, the noise in the output will be nonlinear, it will be correlated, and it will not be Gaussian. So with such architecture of data generation process, we introduce spatial correlation and probably some other important statistics. But the difficulty for us now is that we cannot perform the maximum likelihood optimization, which was used in original Guillemin-Zanna work, because likelihood is not tractable. And we investigate two generative approaches for training. So this architecture, how this data is generated, it's a generative model of machine learning. We always pass white noises into input channel. So in generative adversarial network, we identify the generator as architecture, which I already shown, and also we introduce another neural network, which is discriminator. The role of discriminator is to compare true snapshots of subgrid forcing on the lower and generated snapshots of subgrid forcing on the upper. Based on this, we can train jointly both generator and discriminator to produce new samples of subgrid forcing, which are statistically similar to the training data. Also, we investigate another one approach. It is variational autoencoder. Usually, autoencoder is used as a tool for dimensionality reduction, but here we use variational autoencoder as a generative model. It is possible because the loss function for YE is the evidence lower bound, which is a bound on the log likelihood. And the log likelihood was the standard approach which was used, for example, in Guillemin-Zanna work. So we can train statistical models with this loss function. So loss function consists again of two neural networks. Here the data generation process is called decoder, but it is exactly the same as generator on the previous slide. Also, we introduced encoder, and some explanation for what's going on. The decoder tries to feed data, and encoder provides latent codes for this. Latent space here will be just the noise space, like white noise. And finally, we have a regularization, DKL. It is Kullback labor divergence. It allows us to bound the latent space to be close to standard normal Gaussian. So here I summarize three architecture of stochastic subgrid models which we use. So on the upper we have a model with point-wise uncertainty estimation based on the resolved turbulent flow, but without spatial correlation. And architectures like GAN and YE, they have similar data generation process. They are trained differently, and they allow for spatial correlation. It's important that we use the same building block, CNN, for all three models, so it can be seen that the main difference between them is the difference in the loss function. Okay, now I want to give an example of probabilistic prediction, because for an input coarse turbulent field, I can predict a sample from the distributions. There are many quantities which I can potentially analyze. So let we have some subgrid forcing. It is only a unique field for input coarse and turbulence field. And then I have 3 statistic models. First of all, I can identify the deterministic part of stochastic model. It is conditional mean. So here I show that for GC, GAN, and VE models, the conditional mean is pretty similar. Then I can compute the local standard deviation. These fields look a little bit differently, but main point is that the spatial location of uncertainty where the variance is increased, it is the same in all 3 models, these red spots. Then I introduce the residual. It is stochastic residual. It is unpredictable part of subgrid forcing. To be precise, it is the difference between subgrid forcing S and deterministic model. So this is that part of subgrid forcing which must be simulated stochastically. So as you can see, it is quite complicated field which is difficult to represent by, for example, power law. And in this column, I show the residual which is simulated by a statistical model. So on the upper, you can see that the GZ model, Guemin-Zhang, our baseline, it generates uncorrelated noise. And for generative models like GAN and VE, we have correlated noise, which is similar to the true residual, as you can see here. It was a offline test. Also, we analyze it with metrics, but I hope that this picture is more representative. So now I want to show some online results once we plug in these parameterizations into the right-hand side of the quasi-catastrophic model and perform simulation. On this animation, you can see the reference solution, high-resolution model. And here I show the growth of kinetic energy as a function of time. The black line shows the coarse-net high-resolution simulation. The gray line is a low-resolution simulation. As I already told, when we simulate mesoscale eddies on a coarse grid, so we underestimate kinetic energy because energy cycle is not represented on the grid. The blue line shows the subgrid model, but the coarse parameterized model, whereas subgrid model is optimized with mean squared error. So it's the deterministic model. We can see that it over-energizes the flow. Then we showed our baseline GZ model, where white noise is spatially uncorrelated. So again, we can see that it doesn't improve on top of a simple deterministic model. And finally, green and red lines, these are generative models, and they reproduce the energy level quite well compared to the high-resolution simulation. And also, I want to notice that the laminar turbulent transition, when the energy grows, also better represented by generative models. If look into the snapshots, what the difference between them, we can see that GZ model over-energizes the small eddies, but GAN and VE models, they perform similarly to high-resolution simulation. So we interpret this result as the generative stochastic models allow for to perform simulations which have better numerical stability properties, and due to better numerical stability, we also allow to improve many online metrics. For example, here we show the following metric: distribution error. We compute the distribution of turbulence fields in online simulations like potential vorticity, velocity, entropy, and so on. And we compute the distance between distributions. Here we show that for the coarsest resolution of QG model, the generative approach, there are no legend here, sorry, but green is GAN, red is YE, blue is MSE, and orange is our baseline GZ. So here we show that for coarsest resolution model, the generative stochastic approach allows to improve the online metrics. For higher resolutions, we cannot see the difference between models. So we suppose that the stochastic parameterization is mostly needed for coarsest resolutions. And also we study the dependence of the same distribution metric as a function of the time step. And we show that generative models, GAN and YE, they are less sensitive to changes in time step compared to our baselines, which can have quite large online metrics. So it's another one demonstration of better numerical stability properties. And finally, I want to show what we think is important for our future work. It is inclusion of memory effects. When we were training our model, we were considering every time snapshot independently. And in online implementation, it would mean that the noise in latent space should be sampled again independently as a white noise. And when we study the sensitivity of the same online metric to the correlation time of latent variable, which is parameterized with after regressive time process, we see that the best metric is achieved for uncorrelated in time sampling, which is consistent with our training procedure. And we believe that we need to include memory effect into the training to observe this sensitivity, to achieve best online results for correlated time noise. In principle, it's possible, at least if follow Gagnon work, where they consider conditional distribution also on the previous time step. And here are our conclusions in stochastic models. So we first leverage generative approach for stochastic parameterization. This is GAN and YE. So our idea is to capture conditional distribution and to sample from it. New models can account for spatial correlation of stochastic residuals, as you can see on this plot. And also once we plug in these parameterizations online, we can improve online metrics and also improve numerical stability as shown in this animation. And our future work is including memory effects. And here you can see publication. Maybe a few words about this work. When we developed this parameterizations, GAN and YE, we did not include new restrictions on the models, and so now we can train them on the same data set as GZ was trained. It is a global ocean simulation, and it is another one future direction. Thanks. I'm happy to answer questions.
Thanks a lot, Pavel, and I leave the floor to Andrea for the Q&A session.
Thank you very much, Julian. Thank you very much, Pavel. So, any question? From the participants? I see, and from Alexei, please.
Yes, thank you. Very nice, Pavel. So I haven't read the paper, so I'll just ask them properly. You maybe describe this in the paper, but I mean, the simulations that you show, the coarse resolution simulations, they are also eddying simulations. So yeah, I guess the question is that, you know, is this something that works? You know, have you tried to go to even coarser resolution than you showed here? Yeah.
I see. I tried on resolution 32 by 32. At this resolution, eddy is absolutely not represented. Energy just built up near the grid scale, so I wasn't able to improve anything on this resolution, so I removed it.
Yeah. So is there like, do you have some guidance in a way, like, you know, do you have some I don't know, like some number that gives you, you know, when can you start using this in a way?
Oh, I guess there should be some. These closures are designed as large eddy simulation closures, right? And for large eddy simulation, some part of eddy kinetic energy should be represented. I guess the good number will be 50% of eddy kinetic energy. Once we resolve it, we can apply these subgrid closures. Yeah. If it's less than 50, I don't believe that it will work. And it's quite fair if, for example, look on kinetic energy level, it is approximately 50% of the reference value.
Yeah. Okay, thanks.
Thank you. I see Julian. Have a question.
Thanks, Pavel, for this great presentation. I have a couple of questions. I guess the first one is I'm not sure I got your interpretation of the change in the kinetic energy level with the stochastic component. Maybe it was like if you could re-explain it, that would be great.
You mean this plot?
Yep, the top left plot. Yes.
This should be understood just as a better correspondence between offline and online analysis. Of course, for example, I can train the model, train it with mean squared error. It overestimates energy. I can multiply it by some constant, something like 0.8, and the energy will be just right. But here I have some a posteriori tuning. With generative models, we can represent the energy level without a posteriori tuning. That's it.
Okay, so that's more. You observe that you're able to better capture the energy level, but there's no. So I guess I was probably wondering whether there was a simple like mechanistic sort of understanding the way how the perturbations could foster like could change somehow the cascade and the exchanges between the resolve scales and the subgrid scales. I was wondering you had like a more physical interpretation of this change.
I guess physically everything is pretty simple. When I say that something is numerically is not very stable, it usually means there is a build-up of energy near the grid scale, and it actually happens for this deterministic, for example, model trained with MSE, and the build-up of energy is less for generative models.
Yeah.
And once energy build up near the grid scale, it starts contaminating all scales.
Okay. Andrea, may I continue with my second question?
Sure.
Are there any?
Sure.
Yeah, cool.
Go
so
ahead.
The second question I had is so obviously there are many fine scale state that could that may share the same large scale state, and therefore for a given large scale state there are several subgrid forcing that can, I mean there are several like possible realization of the subgrid forcing that are fully compatible with these scales, and that's what stochastic component, I guess, is trying to capture the fact that there's a diversity, there's a distribution. The way I'm tempted to look at that is to think that it would take a certain time for those fine scale differences to propagate up to the larger scales. And therefore, I would expect that if you pick two different realization of the subgrid forcing, you would get like a typical divergence of the trajectories of the system at large scales, and that it would take a certain time. And I would naturally be tempted to think that this typical time scale is a critical quantity for calibrating the actual nature, structure, and amplitude of the perturbation in the ensemble of possible subgrid forcings. And I'm just wondering whether you've thought a bit about that, and basically of how training a posteriori could help capture this typical timescale for divergence, or whether you don't like share this view. I'd be curious to know what you think of that.
Yes, we thought about time correlation. So it's a question about how to choose the time correlation of the subgrid parameterization. Yeah. As I shown in our results, the optimal time correlation is quite small. It happened because of our training procedure, but it depends on the experiment which we want to optimize. For example, if we would consider the ensemble forecasting for a small period of time, something like 60-90 days, then the optimal time correlation will be larger to improve the spread of the ensemble. We tried this experiments, they're not included into the paper, but the general answer would be, depending on the experiment, the optimal time is different. And also we have a physical time which we can just measure the time correlation of subgrid forcing in our training data. It will be the third time, which is different from these two. I guess by improving the consistency between our models and our subgrid forcing, we can these 3 times will be closer. Now they are quite different.
Thanks.
Thank you. I see hand on from Julie, please.
Yes, hi. Thanks, Pavel, for sharing your work. It's always a pleasure to interact with you and to see your progress. It's more comment than a question, and it's somehow related to the first question from Julien about why you succeed better in not introducing too much energy at small scale. Can you please correct this assessment? My feeling is that your GAN and VAE are capable of learning the effective resolution of your model, which Guillaume-Zana is not able to. And if my assessment you share is correct, then one way to test it could be to play around with the numerical scheme that you use in your QG model, and to ascertain whether, if you choose a scheme that allows bringing the effective resolution closer to the grid resolution, then Guillaume-Zana would be not so much wrong, and yours and yours would be converging to Guillaume-Zana. And if this is correct, then that means that, for me, this effective resolution is partly reflecting implicit diffusion in algorithms, and which is something which we actually don't know what to do with. How do you feel about these?
In general, I agree that it can be connected to discussion of effective resolution. As I already told, it is numerical effect, so it should depend on the numerical scheme. Here we have very specific numerical scheme. It is pseudospectral with numerical filter which removes very small scales, 1/3 of frequencies. I guess this result may change a lot if we will change the numerics. when you say that we can improve the effective resolution, I guess you mean that the band of scales which are represented by the subgrid model, it is wider for GAN and VAE. I guess it's true just by looking on kinetic energy spectrum. Yeah. Thank you for a comment. I will think more about it.
Thank you. I see a question from Francesco on the chat. I don't know, Francesco, if you want to ask about the resolution, or I can just read. It's just it's just asking about the resolution in kilometer or degrees.
It's difficult to remember through value, but I believe something about 27 kilometers for experiments that I show, and it should be approximately equal to Rossby deformation radius, as I remember.
Okay, thank you. Yeah, Francesco, sorry, the microphone does not work. Marcin, please.
Yes, thanks for the talk, Pavel. And my question is about the GAN network. So I just wonder if you had to do anything special to ensure that your generator learns the full distribution of the subgrid forcing conditioned on the resolved flow, whether it, when it tries to trick the discriminator, whether it doesn't like focus on a subset of the distribution where it manages to do it more efficiently. What I mean, it's a question, open question, whether you.
Okay, so your question is about how I was improving the diversity of this distribution and how I was avoiding the mode collapse. Yes. I was playing around this a lot, trying to find some good algorithm. There are a lot of strategies how to do it. I'm using algorithm of mini batch discriminator loss, as it is shown here. It is Adler deep Bayesian inversion 2018. So I use their loss function. Their idea is to consider not only one sample of subgrid forcing, but consider them in pairs. And if two snapshots of generated subgrid forcing, if they are the same, so the loss function is penalized, something like this.
And you found it to work well in this case?
Yes, pretty good. I can show maybe one offline metric if I find it here. So I compute the spread as a ratio between variance of generated residuals R with tilde squared and true residuals R squared. And here I show that spread for GAN model, the green line is close to 1. And for GZ model, it's also close to 1. So both models can capture the variance of subgrid forcing. Variation of the encoder is a little bit worse, so it predicts only 30% of variance.
So was it challenging in your experience in general to, to find the proper metric for the GAN system, or?
Yeah, it was very challenging. So I was trying to introduce this offline metrics into the training process and so on. But finally, I just decided to train for some number of epochs, stop on it and just plot offline metrics, because I do not believe that offline metrics which I introduce, they really reproduce all properties of this conditional distribution, but at least I have 4 metrics.
Do you believe these metrics would be, working well for
I have very general
models?
Models. It's not written in the paper, but the idea of this metrics is very general. I analyze the deterministic prediction, as I call it, the conditional mean. I can analyze it, for example, with RMSE, compare it to deterministic models. Then I analyze individual samples, right? I can analyze PDF, power spectrum, whatever I want, depending on the configuration. And finally, I analyze stochastic residuals. With stochastic residuals, again, PDFs, power spectrums can be calculated. For non-homogeneous flows, I can show spatial map distribution of variance of stochastic residual. So this is my approach is to identify conditional mean, individual sample, and residual, and compare them independently.
Thank you.
Thank you.
So any other question? I have actually very curiosity more because it's not much connected to the work, but when you show the GAN reconstruction of the standard deviation, it seems to discriminate very well which areas. Are you planning perhaps to compare this with the okay, this is a QG model with ensemble spread to see. So in principle, this could be used also to estimate the large part of uncertainty coming from the model. If you've been thinking or planning something to verify also the reconstruction of the standard deviation.
I guess second part of the question I cannot comment it, so I didn't think about it. About first part of the question, you said something like GAN predicts this uncertainty differently. I would say it's very specific example which I chosen for presentation on very high resolution where uncertainty is really small. If we go to coarser resolutions, then these three fields of standard deviation, they are quite close for GC GAN and VE models. And I believe if we have a situation when we can predict only 50% of subgrid forcing deterministically, then these predictions will be close.
Okay, thanks. Yeah, I mean, they look very similar even in the example, but seems like GAN really can spot, discriminate better between low and higher standard deviation. So.
You mean the sharp boundary? I would say it's very specific to this case. I analyzed many resolutions, filters, and so on. It's very specific.
Okay, thank you. So if there are no other questions, I see nothing. So I pass to Julian again for discussion.
Thanks, thanks, Andrea, and thanks again for this talk, Pavel. So we're